So we're talking about Lewis electron dot symbols of atoms and ions. I thought this was kind of a, I guess, yeah, I have pictures of this kind of stuff because the chemical properties of a substance very much come down to the molecular shape. And the molecular shape is going to give rise to boiling points, chemical reactions, a lot of it. So that's really the big goal of all this, is to figure out what the molecular shape of things is just by making little predictions. And it all starts with Lewis electron dot symbols. And somebody, I don't know, I stole this from the internet, and this is really a goal of today, right? That you pretty much write the element formula, then you put dots around it. And it looks like the number of dots you put around it is the number of what electrons? Valence, right? And so these numbers should look familiar, right? Groups 1, 2. What I thought was interesting is look what they did above the nobles. They put a 0 there. Emily, why do you think they did that, whoever did this? Kind of made sense to me after I thought about it. Because it shouldn't be a 0, it should be a what? It should be an 8. But they put a 0 up there because... Yeah, it doesn't need any more to make the 8 the octet. But the nobles, to me, it's kind of like they might have made a mistake, but because it should be an 8. But what I'm thinking of is that it could be the number of valence electrons. And what they're thinking of is that, now, those nobles really have 8 valence electrons. But whoever made it might have been thinking, okay, that the number of electrons, the outermost electrons are there for reacting, right? And to really mess with other bonds and all this other kind of stuff. Well, these noble gases don't interact with anything, not even themselves. So in that sense, oh, they really don't have any valence electrons, right? So there's nothing there. That's maybe their thinking. But technically it has 8, and 8 is the super stable number. So anyway, whether that helps you or not or confuses you more, let's see if we can remember a few things. Megan, give me a chemical formula of any salt. NaCl. Okay, because salts, no, let's say you can't do NaCl because that's table salt. Everyone knows that's a salt. What's a different one besides NaCl? I should add that on there. NaSO4. Okay, now that she's close to naming that formula. What's wrong with that formula? Anybody need it? Help it? A 2 under the subscript for the Na. Okay, so pretty much name any salt. You just have to name a metal and an anion, right? Cation and an anion. Ionic bonds hold the atoms in this salt together, Audrey. And it's a crystal. All these ionic compounds are crystals, and they're held together by ionic bonds. What's an ionic bond? What's the force going on there? What's there has to be some attractive force. What do we think? Sodium ion is starts with the C, cation. Sulfate is a anion. So it would be holding it together. Positive and negative, right? Opposites attract, that kind of thing. So electrostatic forces, that's what's holding an ionic bond together, right? You have a plus and a minus. So pretty strong. Pretty strong. They have really high melting points. Give a chemical formula of a molecule, Dylan. A molecule. So whatever he names can't contain a what? Can't contain a, say it, a metal. CO2. All right, this is when you got to count to 10 in Greek and stuff. So monocarbon dioxide or carbon dioxide. Covalent bonds hold the atoms in a molecule together. Okay, so these things are extremely small, flying around, units of a molecular compound. What is a covalent bond. Actually, it needs to be some kind of attractive force again. What's a covalent bond? It's not an easy question. I think they're still arguing about this kind of thing. But how I picture it is what's the charge on the nucleus? Positive, right? So you have this positive nucleus. Electrons are all negative. Okay, well here's, let's just say that's carbon. I'm going to simplify this. Oxygen's out here somewhere. Who knows what the geometry is? That's something we're going to figure out later. But oxygen has its nucleus. Well, what's between them? These two nuclei. There's going to be a bunch of electrons, right? So that's pretty much, and whose electrons are whose, nobody knows. But carbon's pulled towards the center, oxygen's pulled towards the center. All right, that's kind of the typical thinking of a covalent bond. It might be more information than you need, but okay. Lewis electron dot, or Lewis symbols for atoms and ions. Okay, so it looks like, Steph, how do you write these things? How would you say? How would you write these things? Put the symbol for the element, then what? Put the dots around it. And how many dots do you put? How many valence electrons it has, right? And the easy way to figure that out for most everything is to look where? Anybody? The group number, yeah. So, no biggie. So let's write some Lewis symbols for, so go ahead and write these. Write a Lewis symbol for carbon. Carbon 1 has a +1 charge, and carbon with a -4 charge. It's called carbide. How would you write Lewis symbols for each of those? So Baudi, how did you write the Lewis symbol for carbon? A C with 4 dots around it. And they want you to spread these out as much as possible to prep you for what's coming up, right? So just spread them out as much as possible. And they want them kind of square looking too. That'll help. Okay, carbon +1, Connor. What'd you do for that one?
C, carbon with 3.
3 dots. All right. Now you get knocked, though. You have to do something in addition to this. Does anybody know? However you like to draw brackets, and then write up what charge? +1. He removed an electron. Right. Okay. Kenneth, how about carbide? C -4. Carbon with 7. 2, 4.
Oh, not 6. 8.
8, yeah, because it had 4, but you need 4 extra, so you need 8 total. So 2, 4, 6, 8. Then don't forget the brackets. So -4. Right. So carbon is supposed to form the ion carbide because then it has the noble gas electron configuration of, what is that, neon. So then it makes it really nice and stable. Why would you say, Lorena, that aluminum atom forms the ion aluminum-3 while, well, let's just stop there. Why does aluminum form Al+3? Why would aluminum form Al+3? Right, here's aluminum. I think there's 2 hints. One, Lorraine, is that it has how many valence electrons? 3. So lose all 3 valence electrons. That's one hint. The other hint is everything always wants to have the same electron configuration as what again? Anybody? What up there? The noble gases, group 8. So you lose 1, 2, you're up to neon. So that's why. Right, it had the noble gas core notation of neon. So either answer I think works. So that's why aluminum forms +3. But why would Alyssa gallium, indium, and tellurium they all form just +1. So let's find these guys. Gallium, indium, and tellurium, Alyssa. Here they are. Look, they're right under aluminum. Why would they form just +1? Do you remember? Yeah, it's nice to get to nobles. But there's also, there's noble gas core, and then there's sort of the P. Yeah, if you know how to spell really good, you know what started with the P. P-S-E-U-D-O, pseudo noble gas core. Right? That was D what? D10. So gallium, indium, tellurium, just lose one, then they have D10. If gallium loses one, same as zinc, has D10. Indium loses one, same as cadmium. Tellurium loses one, same as mercury. So they'd form D10s. That's why they just form +1s. Why would you say, Stephen, tin and lead form tin +2 and lead +2? Where the heck is tin and lead? Okay, here's tin and lead. Tin and lead form +2. Exactly, so they go to D10 again. Same argument. What ions would you predict, Mia, for nitrogen? Let's stop at nitrogen. Nitrogen would form what ion? Nitrogen's right there, number 7. Go to noble gases. So you have two choices here, Mia. You can go this way, or you can go this way. Which way do you go? That way. So it'd be N with a -3, because you're adding electrons. N with a -3. Nitride. How about oxygen? Rebecca, oxygen would form what ion? Here's oxygen. O with a -. Yeah, exactly. O with a -2. How about fluorine, Giselle? Yeah, fluoride, F with a -1. Okay. How about phosphorus, Lauren? Lauren. Phosphorus, what ion? Three. Sulfur. Keep going here. Sydney. -2. Sulfide. Chlorine. Emily. Yeah, I got the idea, right? Okay. Why do you think +2? Now these transition metals are all, Megan, transition metals are pretty much everything in between groups 2 and 3 there. It's all the stuff in between. Filling that D shell, filling the 3D, 4D, 5D, 6D, filling those Ds. Picking on Megan. Okay, so and remember these guys, when we were going to name these metals, remember we always had to say the charge in parentheses, right, and give it a Roman numeral. Oh, what happened here? Okay. Where did it go? Okay, so why, Megan, would +2, out of all the possible numbers, why would +2 be the most common one? Could you argue? Yeah, stable at 5 and 2, but I think the reasoning that you're supposed to give is that all these transition metals have one thing in common. They've got the S, the 4s, the 5s, the 6s, the 7s. So there's just 2 electrons there, no matter what the transition metal is. So you can pull those out. So that's why it's a common one. Not a very easy answer. But I'm just saying if you ever have to guess, +2 is a good guess for a transition metal. Write the noble gas core notation for each ion. Okay, Audrey. How would you do this? Well, let's give you some time first. You guys write the noble gas core notation. Oh, this is bored. Let's just go to the boards and answer these. We can answer this stuff together, right? Why pick on Audrey? Let's just go to the boards and Get this stuff done together and we'll be done. So write the noble gas core notation for each ion. So just write your answer up there, see if everybody agrees, then we'll go on to the next one. Write the noble gas core notation for iron 3. Oh, it's not a straightforward one, is it? Write the noble gas core notation for iron 3. So there's an easy way to look at this. Does anybody know what it is? You're really writing the electron configuration. If you just don't look at iron 3 and just pretend it's what element? Pretend it is vanadium. So pretty much just write the electron configuration for vanadium. It's a lot easier to see, right? So write the electron configuration in noble gas core notation for vanadium. What was the word for that? It started with an I. Isoelectronic. Isoelectronic. It's the easier way to look at this. So pretty much just write the electron configuration for vanadium. So find out what the noble gas core is. Good. Argon. And then just keep going from there. Stop at vanadium. And keep going. Argon. Ooh. Nice. I think some people caught it over there. Did you guys catch it over there? Some folks wrote 4s2, 3d3, and then they recognized, oh, they crossed it out and wrote 3d5. Because those half-filled and full-filled D shells are what you're supposed to do every single time.
Wait, what can you say that again?
What's that?
Why is it 3d5?
Because whenever you can form D10, you do it. But then you're also supposed to, this half-filled D shell is also super stable. Because following Hund's rule, there's 5 electrons individually, all in the same direction. Okay. Indium plus 1 should be the same as which element? CD, cadmium. So just write cadmiums, and you'll have it. It's isoelectronic with cadmium. All right, so we wrote krypton, good. What else you got there? 5s2, 4d10. Right? Everybody agree? Okay. Go on to the next one. Write Lewis symbols for the following. Write these electron dot formulas for phosphide and gallium 1. Phosphide and gallium 1. That's magnesium. 1, phosphide. Phosphide and gallium. Oh, that's if you want to write electron dot. That's if you want to write electron configurations. So phosphide, the symbol, and then the number of valence electrons you got that you have in there. So how many dots do you have to have around phosphide? Definitely you have 3, because you have a -3. But you have to add it on to the valence electrons it had there in the first place. And phosphide has how many in the first place? 5.
So is it 8?
So it's going to be 8 total. The hint is, remember, they want that noble gas core notation too. But you should verify it by recognizing how many valence electrons phosphorus has in the first place. It has 5. So if you want 3 extra, you're going to have 8 in there. Don't forget the brackets with the charge. Whoa, this isn't quite right. There's something wrong here. With,
Oh, it's a plus.
yeah. So we've got a P, 2, 4, 6, 8. And then how many dots did you have around gallium? 2. Good. Because you had to remove one. Use a Lewis. Okay, this one might be kind of confusing. Use Lewis symbols to represent the transfer of electrons between neutral atoms to atomic ions with noble gas core configurations. So what I did is I wrote the reaction here for you. So start out by just doing the reactants first. Write their Lewis electron dot structures. Write their Lewis symbols for bromine, calcium, and bromine again. And then we'll see if we can figure out what to do for the products. So first, just start out by writing the Lewis electron dot symbols for the reactants. And they're all neutral, so that means just bromine atoms and bromine atoms and calcium atoms. So start with that. And then we're going to be moving electrons around. Because, well, you'll see it. The reaction will show you. So 2 bromines are reacting with 1 calcium. Yep.
The calcium, when we write this out, is it just going to be the calcium giving each of these 1 electron?
So, yeah, the calcium is going to give this guy an electron. He's going to give that guy an electron.
Okay. Got it.
But you want to write out the reaction, though. So what I mean is like calcium has how many dots around it? 2. So just put 2 dots on there. Wherever you put them, I don't care. And bromine has how many? 7. 2, 4, 6, 7. 2, 4, 6, 7. What we're making, by the way, big picture is, if you want to write calcium bromide, is that how you write it? No. Where do you're missing a subscript. Where are we missing a subscript? Under the BR. It needs to be a 2, right? Because this is a +2, and that's a -1. So we should be making this thing. That's why calcium reacts with 2 bromines. Okay, so we have to show it. Now calcium ends up being remember these are ionic compounds, they got to be ions. Calcium ends up being a +2, bromine ends up being a -1. Because then they match the noble gas core notation. So what you want to do over here is make those ions. So calcium, right, tosses an electron to this bromine, tosses another electron to that bromine, ends up being calcium +2. Those bromines end up being a -1. So just kind of show that, right? It's products. So, no, we just want to show the reaction here. So this guy ends up, I don't know, however you want to show this. You can draw little arrows or something. Change color here. Draw little arrows or something. All right. So you end up with, this guy's just +2. And these guys all end up being -1. Then you can have a whole nother step if you want and just form that thing, but they didn't ask for that. So do the same thing for B, potassium and iodide. How you make potassium iodide. Show the electrons being transferred. Do the same thing for potassium and iodine. So you got it? See what to do? K should just have 1 dot, right? Iodine should have 7. And you just transfer the potassium's electron over there. Okay. You comfortable with that? You got it? You guys aren't writing your answers, so I don't know if you... Okay. All right, let's try this one. For each of the following, write the noble gas core electron configuration and Lewis symbol. So write the noble gas core electron configuration and the Lewis symbol for each of these neutral atoms or their ions. Right? Arsenic, you should be ending up with 4p3 in the end, right? Paul, what did you have as your noble gas core there? Yeah, what'd you put in here, I mean? AR, all right. And then after that, everybody, you had 4s2. Yeah, so we're here, 3d10. And then our 4p3, right? And then arsenic plus 3? Pretty much just erased what? The 4p3, yeah. Just make this a 4p0. You'd have it. Keep going. Silver and silver 1. And if you get that, see if you can figure out which one has a larger radius. Yep. Oh, it doesn't really matter. I don't know why I changed it to silver. Try silver too. You have selenium in your notes. You can try silver too. We have plenty of time here. What did you end up with for silver? Yeah, I think so, right? Because you got to make D10s whenever you can. So I think you have to do that. You have to erase that guy and make D10. Yes, I think that's what you have to do. Yeah, that'd be for silver. Did you see the trick to doing silver? How'd you make silver? D what? What'd you end up with for the D? Because silver should be D9, right? But it's only 1 away from D10. So you make D10. But where did you get that electron to make D10? From the 5s. So you ended up with silver Silver's noble gas core, everybody, is what? Kr. And it was 5s2. What is that, 40? 49. But that's wrong. 5s2. But that's wrong, right? Because you can make D10. So Emily or somebody noticed, I can make a D10. Make that a 1. Make that a 10. There it is. So now, looking at what I'm trying to get you to see out of this exercise is, you can look at this and you can see the number of valence electrons silver really has. You can only pull first, it's a metal. If it's a metal, is it going to lose electrons, or are you going to be adding to it and making anions? Metals only lose. Metals only lose electrons. That's why they're metals. So you can only lose electrons. So how many electrons can silver lose? It can only lose how many? If you look at this. It can only lose 1. Because once you pull out that first one, now you're left with D10. Well, you can't pull from there. You can't pull from the noble gas core. All you can do is lose 1 electron. So the only ion that forms is this guy, silver 1. Okay, so how do you write the Lewis dot for silver? Pretty much, how many dots would you put around it? It's not so clear up here, but it is right here. How many dots would you put around it? Just 1. Just 1. Because the only way to tell is from looking at the electron configuration. That's what makes this tough. And then Ag plus 1. Yeah, I should have nothing. Oh, but don't forget, this is where people screw up. You got to write the brackets and write a plus 1. You're going to lose points right there. And then the electron configuration, what changes? Exactly, so only be 4d10. You can write 5s0 if you want, but you really don't need it there because it's a 0. Okay. And then there's a last question. What's larger, nitride or phosphide? Where are they? Here they are. What's larger? Here, phosphide. Doesn't sound so confident, though. Dylan says phosphide. Steph says phosphide. Why?
The atomic radius goes diagonal down.
Yeah.
And since it's right under it, it's larger.
Yeah. The P's bigger than the N. I totally agree. So you don't even really care about the charges because they're both the same. So don't worry about it. So yeah, just phosphide. What if it would have been? What if it would have been, if this was possible? Then what would you say? You'd say the nitride, because it's those anions, right? That negative charge, because the electrons are what make up the size for atoms and ions. It's electrons. Okay, so that's it. We can handle the exams.